Section 13.3, Factors Affecting Solubility. One of the most important factors that determine whether something is soluble or not soluble is whether you have an attraction between the solvent and the solute. The more there's an attraction, the higher the attraction. So the higher the attraction between the solute and the solvent, the more soluble. So if you have something like a polar solvent, and remember, polar is anything that is positive on one side and negative on the other, and you have a polar solute, okay, which is the same, you're going to have a positive on one side and negative on the other. There is an attraction just because you have negatives and positives, negatives in the solute and positives in the solvent, that will attract. That attraction helps it be more soluble. Remember, solubility is when the solvent rips apart the solute from itself. See, there's attractions between the solute and itself, and if the attractions of the solute is stronger than the attractions of the solute to itself, then it'll all break apart. And that's what solubility is. It's dissolving or breaking apart inside the solution. So if you have very strong attractions, you're going to get more of a soluble than not. If you have no attractions, if there's no attractions between the solute and the solvent, there is no solution. The stuff will just fall to the bottom of the jar and it won't dissolve at all. So solubility, remember, is how much dissolves, whether it dissolves to a great extent or to a very little extent as solubility. So if you were to have a solvent that is polar and a solute that's polar, it not only attracts positives and negative side parts of the molecule, but it can also have something like hydrogen bonding. Remember, hydrogen bonding is when not only do you have a polar molecule, but you also have hydrogens, oxygens, and nitrogens that have leftover electrons in their valence shell. And those electrons can also help pull something else. So if you have a polar molecule that's also hydrogen bonding, say like water, and you have another one such as alcohol that's also hydrogen bonding, then alcohol is very soluble in water. But if you were to put alcohol in something else, like hexane, which is not polar, it would simply float. If you had water and gasoline, you know that the gasoline is just going to float on top of the water. It's not going to dissolve in the water. You could pour gasoline into water, but it just forms two layers, just like salad dressing does. So this brings us to a very saying that you're going to find easy. Like dissolves like. Okay? Polar molecules, polar solvents, let's say, dissolve polar solutes. Okay, so water would dissolve something like salt, or water would dissolve something like alcohol, where it is polar solvent and a polar solute. Non-polar solvents dissolve non-polar solutes. So you have something like acetone, which would dissolve fingernail polish. Fingernail polish remover is not just wet, it has the same attractive forces as the solute. It's more attractive to the solute than the solute is to itself, and so therefore it dissolves. But if you were to put, say, salt, table salt, which is polar, inside acetone, it would just fall to the bottom of the jar. It's not the wetness of the fingernail polish remover that would dissolve it. It's what the solvent is like. So to reinforce, the more similar the intermolecular attractions, the more likely one substance is to be soluble in another. So if you have a polar molecule, it can dissolve in a polar solvent very well. If you have a nonpolar molecule, it would dissolve in a nonpolar solvent very well. This brings us to a question that I'm asked every single year. Glucose, which is sugar, it's a simple form of sugar, one of the parts that sugar is made out of. Glucose dissolves beautifully in water, but glucose is not a polar molecule. Why does it dissolve so well in water? Because it has some parts to it that are like these hydrogen. There's a glucose molecule has some hydrogen. These are alcohol groups, and it has 5 alcohol groups in each molecule. These alcohol groups are polar, and they are on their own they would be polar, and they can hydrogen bond, and water hydrogen bonds. And so water can surround this entire molecule. Now, it doesn't break up. It's not like salt where it would dissociate into positives and negatives. It's one molecule that stays by itself, but because of these hydrogen bonding between the hydroxide molecules, this OH, in a part of the molecule, and the water can surround it. And so you can put sugar in water and it will dissolve. The sugar kind of goes away for the same reason that salt would go away. But salt's actually breaking apart and the sugar is not. Sugar is just being surrounded. Even though it's a large molecule, the water completely surrounds it. Now if you look over to the left, okay, this is cyclohexane, which looks basically the same as the glucose, but because it doesn't have these, it just has hydrogens, there's nothing for the water to grab onto. So it can't be dissolved. It will just sit on top. So cyclohexane is just a lot like gasoline. It's a hydrocarbon, and it would just sit on top of the water and not dissolve at all. Another really interesting part to this is once you get to physiology and anatomy class and you start studying vitamins. Vitamins are very large molecules, organic molecules, that help with a body function. So for instance, vitamin D that you get in milk will actually help store calcium into your bones. It's one of the things vitamins do. There's many, many things vitamins do. But vitamins, there's 2 types of vitamins. You have fat-soluble vitamins, and you have water-soluble vitamins. Water-soluble vitamins are soluble because there's lots of these OH groups, just like the glucose, that water can surround and grab onto. In, say, vitamin A, this is vitamin A, there's only one hydroxide, and because there's just one, that's not enough for the water to hold onto, and so it doesn't dissolve in water. Well, vitamin A, because it doesn't dissolve in water, can't dissolve in the body fluids. It dissolves in fats, but it doesn't dissolve in body fluids. That means you could eat too many carrots and not be able to flush this vitamin A from your body. It would store in your fat, and you could actually poison yourself. You could eat too many carrots and actually die. Carrots are poisonous if you eat tons and tons of them. But say vitamin C, you couldn't eat too many oranges because the vitamin C in the oranges are water soluble, and if you ate too many oranges, it would simply just dissolve in your body fluid and be flushed by your kidneys. So it's pretty cool. You can think about that. Even it has to do with body functions, because everything in your body is chemistry. This picture is actually in the wrong slide. I put it in the wrong slide, but I love the picture. Let me explain. This is sodium chloride dissolved in water. So the sodium, which is positive, the oxygen part of this water is oriented to where it completely surrounds the sodium. Okay, this would be called hydrated or solvated. The solvent, in this case water, which has special name hydration, is where the water completely surrounds that sodium. The chlorine is negative, and so the negative side, which is over here, the oxygen, stays away from the chlorine, and the positive side, the delta positive side, which is the hydrogens, will orient themselves towards the chlorine, and they surround it to where they stay away from each other but surround the chlorine. So in this case, 1, 2, 3, 4, 5, 6. 6 oxygen heads can surround a sodium. In this case, 1, 2, 3, 4, 5, 6 hydrogens can surround a chlorine. But because these hydrogens are not so dense, you've got this is a bigger circle because the chlorine is bigger. It's pretty cool. There's geometry involved in this. Any case, this section is on gases. Gases can dissolve into liquids. Gases can dissolve in other gases. You can see that you can have different solutes inside different solvents. But if you were to have a gas dissolved into a liquid, the solubility of that gas would be based upon the temperature. Now, how we saw that the higher the temperature, the more solids can be dissolved. So you can have more sugar dissolved in your tea if it's hot tea than cold tea. It works exactly the opposite in gases. Okay, the higher the temperature, the less gas is dissolved. Gases are dissolved. So gases are dissolved with temperature change and with pressure changes. So the higher the temperature, the less gas is dissolved. That's why that if you have hot water, you're not likely to catch a fish. Hot water will float on top of cold water, and if you want to go fishing, you want to make sure that you're fishing down into the cold water. But if you had complete hot water on top of cold water, you could actually poison all your fish because the oxygen which is in the air can't get to the water down below the hot water. Okay, so that's a problem, and it's actually considered, temperature is actually considered pollution in water. You also can see that gases can change under pressure. If the higher the pressure, okay, so this is two different things you need to kind of put in your notes. The higher the pressure, the more gases. I wrote more as with an S, I don't know why. More gases are dissolved. That's why if you want to make Coke, you take water, you put some sugar in it, and then you put whatever spices are in the Coca-Cola, and then you carbonate it. You put carbon gas at high pressure, and that carbon, at high pressure, the carbon dioxide goes into the gas, and then it's sealed. Once it's sealed, if you break the top, if you open the bottle, all the pressure drops, and then the gases that are stored in will drop and come out as bubbles. So pretty cool. So let's look in a little more detail. The solubility of liquids and solids don't change with pressure. So if you put sugar in your tea and then you put it under high pressure, it's not going to change anything. But if you put gas into a liquid and you change the pressure, the higher the pressure, the more gas will dissolve into the liquid. Okay? That's why, believe it or not, you shouldn't pop your knuckles. Popping your knuckles are essentially popping the gases that are dissolved in liquid. You've got gases dissolved in little bags in between your knuckles, or in between every bone. Okay, you certainly don't want your bones to rub together, and arthritis is when they're rubbing together, and it's very painful. If you have little bags of synovial fluid in between the bones, and you pull your knuckles apart, you're increasing the volume of that little bag, and as it decreases increases the volume, you drop the pressure. And if the pressure drops, the bubbles that are dissolved in that liquid will come out, and that's what you hear when you're popping your knuckles. You're actually hearing the gases escaping from solution. It also can cause some scar tissue, so you really don't want to do it, even though it's funny. Henry's law is the law that you're talking about when you talk about pressure. So the higher the pressure, the more gases dissolve. The lower the pressure, the less gases dissolve. This is called Henry's law, and this is how you would make soft drinks. Also, we've already seen that temperature affects solids, okay? So if solid dissolved in, let's say, in liquid, the higher the temperature, the more solid dissolves. But in gases dissolved in liquid, the higher the temperature, the less gas is dissolved. Okay, so you're going to see normally that the solubility of a solid will increase with increasing temperature, but the solubility of a gas decreases with increased temperature. So this is the gas one. As the temperature increases, the solubility decreases of gases. So warm Coke is not very bubbly because the warmer the Coke, the more the carbon dioxide comes out. Even if you were to take cold water, the water you get under the tap, and you warm that and you just put it in a glass and let it come to room temperature, you'll see bubbles along the inside of the glass that used to be dissolved gases inside the cold water, because less gas can dissolve in warmer water.